okay. I can enjoy.
Yeah, that's okay.
Enjoy the break.
Yes.
Okay. Good morning, everyone. Welcome to East Colloquium number 38. Today we have David Mota. Okay, here with us. So he's going to give a talk on a topic nonlinear cosmological probe on screen gravity theory beyond general relativity. Sorry, okay. So yeah, if you're ready, please.
Okay, thank you very much. Once again, thank you very much for the invitation, especially to Kanti. It's really a pleasure being here to visiting you, to meet the research group, especially the students. I hope you have learned something from me in the last few days. So today I will finish my week here with the colloquium. Um, the colloquium is going to be kind of a continuation of the lectures that I gave. So I'm assuming that your background and your knowledge, that you learned something during my lectures, so you will understand this colloquium. But I will review some of the items in case there's some new people here, which I can see some new faces. So yeah. So I'm going to talk basically about non-linear logical tests of theories of gravity beyond general relativity. So I will focus, during my lectures, I mainly focus on linear structure formation, so very large scales tests. In this colloquium, I'm going to tell you about non-linear ones, so small scales, galaxy and galaxy cluster scales, so much, much smaller scales. And I will, hopefully at the end of my colloquium, you will understand why in my opinion, these are fantastic probes to test not only gravity theories beyond general relativity, but in particular the screening mechanisms, which I believe now you know what is a screening mechanism, but I will review for the ones who didn't attend my lectures. Okay, so for all of you, I think at least the students know that I'm aware that when one studies gravity beyond general relativity, we need to be aware of the many tests and experiments that already are and have been there for several decades, where we try to test Newtonian gravity, general relativity beyond, and theories beyond gravity, beyond those, in, for instance, laboratory tests, and all of them, they basically confirm general relativity and Newtonian physics. So there's no indication whatsoever in laboratories that we should look at the gravity theory beyond general relativity. So there's no motivation in laboratories and experiments we perform on Earth. And in particular, there's very strong bounds if you do gravity beyond general relativity from the equivalence principle. And I will tell you a little bit more on the equivalence principle later on. But basically, the equivalence principle says that any particle in the universe should have a universal force. So it should just feel the metric of space-time, and all the particles in the universe should just feel the same metric. But those tests of theories beyond general relativity, they are not only done in laboratories, but also in the solar system. And again, in the solar system, all the tests that we've been performing up to now, they also confirm general relativity. In particular, there's the microscope experiments, the satellite, where they tested the equivalence principle again, now in space, so much better precision and control of systematics. And again, the microscope satellite and also the Cassini probe basically tells you again that general relativity seems to be the correct theory of gravity. So if you have any modification of gravity, you should have general relativity in the solar system as well. And we did tests even beyond that, because we even went to astrophysical scales with the binary pulsars, as I told you about in my lectures, that even several decades looking at the data of how the orbit of the pulsars decay due to the emission of gravitational waves, they fully confirm general relativity again. So the solid line is general relativity, the dotted points, those are the data with the error bars. So again, general relativity is the correct theory of gravity, even at astrophysical scales. And then, as I told in my lectures, even in 2015, when we discovered, and we have been detecting now gravitational waves, or the merger of compact objects, black holes and neutron stars, again, the waveforms that we are seeing, those are again, are in agreement with general relativity. So the big question maybe for people who don't work in theories beyond general relativity is why there is a group of people here at this institute and some people around the world like me who still believe it's worth spending our time studying gravity beyond general relativity. And for that, I need to show you where we have been testing general relativity. So what is in the parameter space, this is what this plot is going to be about, where in the general parameter space of testing of gravity, where did we perform these tests? So let me explain. So here, what I have in the y-axis is called the Kretschmann scalar, which you can think of it as the curvature of space. While in the x-axis, you have the potential. Okay, the usual potential. So these are two scalars. So this is one way of parameterizing gravity. There are several ways, of course. But this is just one way. With two scalars, we can somehow give you an indication where we have been testing gravity. So the potential, you can think how deep the gravitational well is, while the Kretschmann scalar, you can think how strongly the field, the gravitational field, changes throughout space. Now, if you can see, this is a scale which goes from, there's 50 orders of magnitude here on the y-axis, and there's 12 orders of magnitude of range in the x-axis. Okay, so it's a huge parameter space. Just to give an indication, if you look at the scales from the DNA, from an atom, molecules, all the way to a human being or a whale, there are 10, you can't see the number, it's too small, but there are like 10 orders of magnitude here. So this is, it does not even fill the whole x-axis in there. So 10 orders of magnitude. So you can imagine that the physics that we describe, we used to describe, for instance, the behavior of fluids or animals or people, the Newtonian gravity physics, is very different from the physics that we used to describe molecules. That's going to be quantum mechanics. Yes? So it's a very different physics. So this is just to tell you that when we go from these scales, it's a huge scale. If you put this on the y-axis, it's even worse. All these 10 orders of magnitude scales, they fit there. So as you can see, this parameter space is really, really, really big. Okay? This is the first thing I want to tell you. So it's a huge parameter space. Now, where we've been doing tests of gravity, the ones that I told you about. So if we look at tests of gravity that we perform in laboratories on Earth or in the solar system, those tests are usually here. So these are the ppn constraints, you know, the gamma parameter that I told you about in my lectures, with the Cassini probe, atom interferometry, those neutron bouncing that I told you in my lectures. All these laboratory constraints, they are in this region of the curvature and of the gravitational well. So these are the regions that we have been probing. When we want to go and test astrophysical system like the binary pulsars and black holes, that's the region that we are coming. We are coming to strong gravitational wells, so order 1, that's when the black holes form. And all the experiments like LISA, the pulsar time array, and the future experiments like the Einstein telescope, etc., all these experiments that we have been doing, like seeing the Sagittarius A star, the merger of binary pulsars, merger of black holes, etc., they all come into this region of the parameter space. And this is the place where, up to now, we don't see any evidence whatsoever for the breaking down of general relativity. So general relativity works very well in here. There's no motivation whatsoever. However, as cosmologists, we have also been studying and doing observations to our universe. And those observations usually, before that. So something that you should be aware of is that the scales that we have been probing is like scales of compact objects. So they are going to be like the size of the sun, or about 1 astronomical unit if I'm doing experiments on the solar system. Yes. But we have also doing tests at cosmological scales, so much larger scales. So we go to kiloparsec scales when we look at galaxies, we go to megaparsec scales when we go to galaxy clusters, and even further. And those scales, we are starting to basically probe this region of the perimeter space. And those are the tests that we do, for instance, when we have the Planck satellite measuring the cosmic microwave background radiation, when you have the Sloan Digital Sky Survey, or now the Euclid satellite measuring galaxy distributions in the universe. These are the scales that we are now probing, the lower part of this diagram. And remember, this is a huge perimeter space, yes? So, just to give you an idea as well, so we believe general relativity works very well. It's for instance, the Big Bang nucleosynthesis, so when the universe was about a minute old, so when Big Bang nucleosynthesis happened, the density is more or less here. So you can see these regions, the density is very high, the density of the universe. That's the regions where we believe general relativity works very fine. Here, when we go for the last scattering surface, when the CMB, we are coming down to this kind of densities, this region of the perimeter space. That's also quite important. Now, the big surprise is that when we do these observations, we cannot really interpret the results without introducing the dark matter component and the dark energy component. So here, we dark energy. General relativity works fine with the standard model of particle physics. But when we come down here, in order to explain what we see in the cosmic microwave background radiation, galaxy distribution, rotation curves, cluster properties, we need to introduce dark matter and dark energy. And there's more, because also in this region, we know that we have the GR singularity. So we have the formation of the black holes. So what people start to wonder is that, well, this is a very strange region of the perimeter space, because we cannot, in the standard model of particle physics and general relativity, to explain this phenomena. And people start to wonder, maybe in this region of the perimeter space, we have the modified gravity. And that's basically the main motivation for that. Now, what people have been doing then, since the discovery of the evidence for dark matter and dark energy, people have been doing a lot of tests, cosmological tests, for trying to find what is the true nature of gravity in this lower part of the perimeter space, and this here, where we have like, where the general relativity breaks down, and we know it breaks down inside the black holes. The problem comes when we try to do cosmological tests of gravity here, in this lower part, is how do we know we are seeing signatures of modified? How do we know we are seeing signatures of just a dark energy or dark matter component? These are highly degenerate. So of course it's very promising to look at this region of perimeter space, and I do not discourage my colleagues to do that, but it's going to be always extremely difficult to find whether it is a dark matter particle modified gravity or it is a dark energy field or modified gravity. Extremely difficult. But still, of course, worth doing it, because that's the region where we believe there's something wrong there. The other part of the perimeter space, which I like a lot and I think is very promising, is to look at a place where we know general relativity breaks down, which is from the limit on the formation of the black holes. The problem here that arrives is, up to now, most of the tests of probes of gravity, we need to have very specific templates to look at the data. So we just don't take the data, we take the data and we confront it with some very specific templates. And up to now, our templates are basically GR, general relativity. So we are always conform in general relativity. So we need to build up templates for modified theory of gravity to really use effectively the data coming from there. But let's look again at this perimeter space. And what we know is that if we're going from the low curvature regime to the high curvature regime, and if there is modified gravity, one thing that we need for sure to have is a system or a mechanism which will screen the modified gravity as we go from the low curvature regime to the high curvature regime. So we need to have a screening mechanism that hides these modifications of gravity when we come from this region of the perimeter space to that region of the perimeter space. In the same sense that we go from Einstein general relativity in the weak field limit to Newtonian gravity on the weak field limit. Yes? So we need some kind of screening. And this screening mechanism will happen in this region of the perimeter space, which is a completely desert there. Well, at least is a much less probe desert. And this region of the perimeter space, which is about 10, 15 orders of magnitude, so it's a quite big region, is the region of the nonlinear probes, nonlinear cosmological probes. And that's the region where we have galaxies and clusters of galaxies. So if we want to try to detect a screening mechanism, what I'm going to try to tell you in this talk is that there are some very promising nonlinear tests of gravity which can tell you whether there is a screening mechanism or not. So this is what my talk is going to be about, is basically to try to probe, which means try to detect screening mechanism and signatures of modified gravity in this region of the perimeter space. Okay, so as I saw in my lectures, there are many different types of modified gravity, and of course I cannot cover all of them. Here I'm going to focus on scalar tensor theories of gravity. So I will just introduce, as you saw my this slide before, an extra degree of freedom. So a scalar field on my gravity sector, and as you all know now from my lectures, every time you introduce an extra degree of freedom, what you will get the fifth force for our particles. And the fact that I'm introducing this extra degree of freedom, there are several consequences that appear in my universe. One of them is the variations of constants. So the constants of nature, they're not constants anymore. So what we thought, we think of the G, the gravitational constant, as a constant. It won't be a constant because we have this scalar field evolves in the universe. So G, the gravitational constant, is going to be a function of n space. And it is the same for the mass of the particles, the mass of the electron, the mass of the proton. All these will change in time. Okay, so of course, when we do these kind of theories of modified gravity, you need to be sure that you are within these constraints. And a very, very important consequence, that's the one I'm going to focus here today, is the violation of the equivalence principle. And I will tell you how we can test that using cosmology. Very good. So the whole idea on this extra modified gravity with an extra degree of freedom is that you introduce this field. So you introduce fifth force, yes, and that leads, as you know now, to the modification of the Newtonian. So particles feel the usual Newtonian gravity plus what is called the Yukawa correction now. And all the tests that we've been performing on laboratories, on the solar system, also black hole, we don't see is Yukawa correction, as you know. So again, just a slide from my lecture. If we have a scalar tensor theory of gravity, we have the Yukawa correction, and we want basically to hide, to screen away this Yukawa correction in our laboratories and solar system. So the way to do that is to look how we can basically make this Yukawa correction go to zero. So for a general Lagrangian, for not completely general, but quite general for the purpose of this colloquium. So if I introduce my scalar field, which has a non-standard kinetic term, a self-interacting potential, and the coupling to matter, this dg, which couples to the trace of the energy momentum tensor, what you have is a general Yukawa correction given by this form. Yes? That's the general one. So what laboratory tests of gravity tell you is that this Yukawa correction does not exist in our laboratories. So we need to screen away these Yukawa corrections. We need to hide it. And the way to do it, as now you know hopefully quite well from my lectures, the one who attended, is basically to either you make G, the coupling between the scalar field and matter, very weak. So if this guy goes to zero, then the whole Yukawa correction goes to zero. So that's one possibility. The other possibility is to make the mass of my field extremely large in laboratories or in the solar system. So this exponential goes to zero, and the whole Yukawa correction also goes to zero, and we can hide our field. Or the other possibility is to have a field with a very large inertia. So the non-standard kinetic term, which comes as 1 over z here, if it's very large, that will make my Yukawa correction to go to 0 as well. Okay, so I'm sure the students, if you listen to my lectures, you know about that. Very good. So the way we screen modify gravity can be classified, as I said, like you can have the chameleon mechanism, which screens using the mass. You can have the symmetron and dilaton mechanism, which screens playing with the strength of the coupling. And you have also the camouflage, if you play with the kinetic term, or you can have the Weinstein screening mechanism if you use the curvature. Okay. So what I'm saying is that there are several screening mechanisms. I'm not going to look at all of them, but the conclusions that I'm taking from this colloquium, that you will see my results, they can be generally applied for these screening mechanisms. Okay? And the reason is that I want you to remember that I need to have whatever mechanism I choose, what I'm going to do is to screen my modified gravity from low curvature regimes, from low density regimes to high density regimes. Okay, so every time I'm coming and do experiments in high density regimes where the curvature of space is very large, then one of these screening mechanisms needs a role. Okay, I am of course going to show you results very specific, and I'm show you results very specific for the symmetron screening mechanism. Okay, so I'm going to remind you again what is the symmetron screening mechanism. So the symmetron is basically a scalar tensor theory where we have a standard kinetic term, a self-interacting potential, and a coupling between my scalar field and my standard model fields and the dark matter as well. Because I'm assuming dark matter to be the standard cold dark matter, like a WIMP particle. So for the symmetron, I have to choose a coupling, which I'm choosing to be this quadratic form. And what I will do, this coupling will play the role of the coupling in my Yukawa correction. Is alpha there. And that's the one that I need to make it go to 0 as I come to a high density region like the Earth, for instance. So how does it work, my chameleon, my symmetron mechanism? It works that when I compute the Klein-Gordon equation, the equation of motion for this scalar field, I see that my scalar field follows the behavior of this effective potential. So this is the effective potential of my scalar field, of my symmetron field. And we have a phi squared term coupled to the trace of the energy momentum tensor that just rho, the energy. I'm assuming non-relativistic matter because the relativistic one basically trace is equal to 0. And I have two free parameters of my theory that comes from my self-interacting potential, phi to the 4 term in particular. Okay, so what does it mean? It means that when I'm in a region of the universe like the Earth where the density is very high, the term that dominates my effective potential is a phi squared term. And so my effective potential is just a parabola, and my scalar field comes down to its minima, of course. Comes down to its minima, becomes 0, and if the scalar field is 0, that means that my A of phi becomes equal to 1. And if my A of phi, my coupling to matter, is equal to 1, then it means that my scalar field decouples to matter. And so on Earth, I can do whatever laboratory experiments I want, that I won't see my scalar field in my experiments. I won't see this phi force because the field decouples on my experiments. As I go to lower dense regions, so if I go far away into the universe, to voids, galaxy clusters, etc., the effective potential changes shape, just like in a Higgs kind of symmetry breaking mechanism. And my scalar field will take a vacuum expectation value, which is now is non-zero. Can be either positive or negative, but what will mean? It will mean that in low dense regions, I have that my coupling to the energy momentum tensor is not 0 anymore. And that means I have a phi force because my field is alive, is strongly coupled to matter, and that means matter will feel a gravitational strength which is larger than just G. So the symmetron, basically, sorry, I wanted to show you something else. So basically, the symmetron screening mechanism is a mechanism that dynamically plays with the strength of the coupling of the fifth force, either when it is on Earth or near a pulsar or a black hole. The scalar field completely decouples from matter, so you won't see the effects of this extra degree of freedom when you look at production of gravitational waves or the binary pulsars, the decay due to the emission of gravitational waves. But when you are in low dense regions of the universe, basically the scalar field is alive and you have the fifth force in there. Okay, so what we have then is what I told you before. If there is a fifth force due to this scalar degree of freedom, then it means we should look at structure formation at the universe. Because particles in the universe, the dark matter particles, the baryons, all structure in the universe should feel an acceleration which is enhanced. Because the acceleration of each particle in the universe will have a GR term due to the Newtonian potential, and also will have the fifth force, an acceleration due to the fifth force. And structure formation will be affected quite strongly, as you can see in this example between when you can compare general relativity to the symmetron. Now, during my lectures, I told you about the large-scale structure formation, but in these lectures, I want to tell you about small-scale structure formation effects, because those are much more promising, and those can give smoking guns. Now we know what smoking gun is, like an evidence for a screening mechanism. Okay, so let's take a look to the velocity of galaxies in a galaxy cluster. Now remember that matter in the universe will feel the acceleration, the Newtonian acceleration, plus the acceleration of my fifth force due to my scalar degree of freedom. So that means if I take a cluster made of galaxies, nowadays looking at redshift probes, I can do spectroscopy and I can measure very accurately what is the velocity of galaxies in a cluster. So I can make a plot of the velocity of the galaxies versus its distance, with like the galaxy rotation curves that I can do for stars that I talked about yesterday in my public lecture. I can do the same for galaxies in a cluster. Now, if I have a screening mechanism in my modified gravity, something that we need to be aware of is that if I have a galaxy cluster usually will have a core which have very massive clusters, many galaxies around it. And as I go to the outskirts, I will see less and less galaxies until I reach the edge of the galaxy cluster. So that means that my fifth force will be screened usually in the center of my galaxy cluster because the density is high. But as I come to measure properties of my galaxies in the outskirts of the cluster, the fifth force will start to appear because we'll be unscreened because the density is much lower. Okay? So I should expect that if I look at the galaxy on the outskirts of the galaxy cluster to be strongly accelerating, to be moving very fast, much faster than expected in general relativity, while galaxies which live in the center of my cluster, they should move as fast as in general relativity because the fifth force is screened. So we did some simulations for different symmetron models. So each line represents a different symmetron model, each color. And we did these big N-body simulations, and we identify halos. So the example here is for a halo, a dark matter halo, so a galaxy cluster, which has a mass between 13.5 to 14 solar masses. So it's a huge cluster, in fact. And in the y-axis, I'm plotting the velocity of the galaxies with respect to lambda CDM. So I'm comparing how much faster do galaxies move in the cluster. And here on the x-axis, I'm plotting basically the distance from the center of the cluster. So we are here in the center of the cluster. As I reach to 1, I'm going to a radius, which is more or less the virial radius of the cluster. It's called also R200 because it's the the edge of the cluster where the density drops 200 times the critical density of the universe. So you can think of, this is the same as the galaxy rotation curve that I showed you yesterday on my public talk. Yeah? So what we see here is that galaxies which are at the center of the cluster, so galaxies which are at the center of the cluster, their velocity is very similar to the lambda CDM one, to general relativity. While galaxies that are at the edge of the cluster, their velocity is much, much higher than the general relativity cluster size. And this is precisely what we expect. Because remember, for the symmetry model, as I am on the outskirts of the cluster, the density is much lower, so the fifth force is very strong. It's stronger than in general relativity. So the velocities become very high. As I come to the center of the cluster, my fifth force is screened, and so the velocities of these galaxies in the center of the cluster are pretty much the same as in general relativity. Now, the smoking gun that appears here is this one. Is if I look at the cluster, I do a measurement of the galaxy rotation curves, and I see there is this difference. There is this slope where galaxies in the center of the cluster, for some reason, they just confirm general relativity. And galaxies at the edge of the cluster, they don't confirm general relativity because they are moving much faster. That would be the smoking gun for a mechanism. And the reason is because if I had a modified theory of gravity or a dark matter component that would be always there, there's no screening mechanism, this curve, all these lines should be flat, should be horizontal. If there is no screening mechanism, it means that the galaxies at the center of the cluster, they should move very fast, but also galaxies at the center, on the center of the cluster, they should move as fast as galaxies at the outskirts of the cluster. There is no screening mechanism. All the galaxies, they just feel this fifth force. So this is a quite nice way to break the degeneracy. But there's even more to compare. If now I look in my universe, I look at very big clusters, 10 to the 14 to 10 to the 15 almost, 10 to 13.5 to 10 to the 14, and 10 to the 13 solar masses to 10 to the 13.5, and I do the same analysis for different models, I can see that the maximum velocity that I can reach at the end of the cluster for a very big cluster is about 25%. If I go to a lower cluster, goes up to 35%, and if I go to a smaller cluster, it goes up to 40%. And again, the reason is because if clusters, they have, the screening mechanism is already working on them. So the acceleration of these galaxies at the edge, it's smaller than, for instance, in a very small cluster. And again, the feature for the smoking gun is to look at the universe at different clusters, different masses, and we see that deviation from general relativity should be dependent, should be environmental dependent on the mass of the cluster. So we shouldn't have the same curves with the same deviations throughout different clusters. And this would be something that will be quite unique because you can't mimic these kind of behaviors just with a dark matter model or dark energy model or a modified theory of gravity without screening. Okay, so this was one of the first that I have. The second one that I'm going to tell you about, it's the equivalence principle test. So this is a very nice test. I like it because it's very easy for the students to understand. So at the Newtonian gravity level, we have that the definition for inertial mass, that's the one just comes from the Mars that is defined as the proportional constant between the force and the acceleration. This is what we call the inertial mass. So how a body prevents from moving given if it's hit by a force. The other one, we have the gravitational mass that comes from Newton's third law, where the gravitational mass, you can think of it as the charge for the gravity interaction. Okay? In Newtonian gravity and in general relativity, they are the same. The inertial mass and the gravitational mass, they are the same. So it says the charge for the gravity interaction is the same as the inertial mass that we put it in there. So when we perform these experiments in laboratories, we don't see any difference from that. Now, what about in cosmology and in astrophysics? How do we test the equivalence principle in there? Well, we need to do that by measuring the mass of objects in the cosmos. So if I have a skeleton theory, again, I'm going to focus on the symmetron, or in general, in fact, how do I measure the mass of an object in the universe? Well, one way is to I have a given massive object, for instance, which has a given mass. I want to know the mass of that star. One way is to have a test particle moving around the star, for instance, a planet, moving around the sun. And from measuring the acceleration of this test particle, I can infer, in the orbit, I can infer what's the mass of that object. So that's one way that I can look at a galaxy or a cluster of galaxies. I can infer the mass of my cluster of galaxies by measuring what's the acceleration of the galaxies inside the cluster or the stars inside the galaxy. So that's one way. The other one is by using lensing. So you basically look at how photons propagate through the gravitational well of that massive object produces, and you can see how the photons are bent, how light bends, and from that you can infer what's the mass of this object there. So these are basically two ways that physicists can use to measure, for instance, mass of objects in our universe. Okay, so in order to do that, from the theoretical point of view, what you usually do, you want to parameterize the curvature of space that is created because of this massive object. So usually you have your metric, you perturb using your Bardeen potentials, yes, in there, phi and psi. And the acceleration of your test particle is basically the gradient of your 0,0 component of the metric. And for the photons, what photons really feel is this devial potential. That's the name of it, which is basically the sum of the two Bardeen potentials. So basically you have to measure the 0,0 component, and then you have to measure the II component or IJ component and sum with the 0,0 component to get the photons on the lensing. So in general relativity, what you have is that you have the Newton-Poisson equation, where basically the 0,0 component of the Bardeen potential is just sourced by the mass distribution, so that's going to be that one. But now, if you have the symmetron, or a modified theory of gravity with an extra degree of freedom, you have this extra term there, which is sourcing the Bardeen potential there. Just like in my lectures yesterday, I showed you this example explicitly for the F of R gravity. Now this is just for the symmetron, but it's very similar. You have the Newtonian contribution of the mass plus the fact that you have an extra degree of freedom and how this field sources the 0,0 component of your metric. In the symmetron, it can be shown, I won't be showing you here, that in fact, when you do when you calculate the solution for the Bardeen potentials, you have that phi is just a phi Newton plus a perturbation of my scalar field, in particular my coupling, and the psi, the IJ component, is just the Newtonian minus the perturbation of my coupling there. So what does that mean? When you calculate the Weyl tensor, the Weyl potential, sorry, which is the sum of the two of them, I just get that the Weyl tensor is just the Newtonian one, because they cancel each other. So what does this mean? Is that photons, in fact, even in modified theories of gravity, I should be more explicit, in conformal theories of modified gravity, they feel the same potential as in general relativity. And this gives me a fantastic way of testing the equivalence principle. Why is that? Because then I can look at object, this is a galaxy cluster, and I can use lensing methods looking at photons, how photons are lensed by a galaxy cluster, to try to infer what's the mass of this galaxy cluster. And I will call this mass the gravitational mass using lensing methods. And due to conformal invariance, as I said, as I showed you there, and that's the theories of modified gravity that I'm focused on, the null geodesics are in fact not affected by the existence of this scalar degree of freedom, because the lensing potential is just the same as in general relativity. So when I look at the cluster and I do a lensing analysis to infer how much mass this cluster has using lensing, I get the same result. My results are independent of my theory of modified gravity. Now, when I'm going to look at this cluster and I'm going to infer the mass of the cluster by looking how fast galaxies in the cluster move, then I'm looking at the so-called kinematical mass. And that's basically a measurement of the inertial mass. Now, what I'm doing, I'm looking at the velocity dispersion of galaxies in a cluster. And the mass of the cluster, the kinematical mass, you can imagine like in a spherical symmetry, it's just v squared over r. That's going to be proportional to the Newtonian force. Galaxies in a cluster will be accelerated cluster with the Newtonian force. But if there is modified gravity, they will also feel the fifth force of the field. So that means if I take a cluster and I use dynamical methods, so I use the acceleration of the galaxies to infer the mass of the galaxy cluster, then I will get a number for the mass which is larger than if there is general relativity. So my equivalence principle test is to compare this inertial mass with the gravitational mass. So compare the kinematical mass to the lensing mass. And that's my equivalence principle test. So I'm going to compare the dynamical mass with the lensing mass for the same cluster. So I'm going to look at the same cluster, do a lensing experiment, calculate the lensing mass, and then later, taking the same cluster, doing an experiment calculating the dynamical mass, and take the ratio of them. So in general relativity, due to the equivalence principle, they should be just this quantity, the ratio between them should be just 1. Yes? Because of the equivalence principle. In modified gravity, they should be different, so we should see a difference there. So what we did, again, these are from simulations. I will show you observational results later. We did some simulations within the symmetry model and the f of r model, and in fact the DGP model as well. And we compared the kinematical mass to the lensing mass. That's the ratio, -1. For clusters which have a mass of 10 to the 13, 10 to the 14, and 10 to the 15 solar masses. And each line is basically a different model for the symmetron, where this black line here, basically this is just general relativity. So as you can see, for general relativity, it's all around 0. And that's because the equivalence principle is satisfied. The lensing mass and the dynamical mass, so the inertial mass and gravitational mass, is just the same. So you don't see any violations of the equivalence principle. But you can start to see there are violations of the equivalence principle for other symmetron models. And something that you can see, if you look at very small halos, so if you look at the galaxy cluster with only 10 to the 13 solar masses, you have violations of the equivalence principle. The lensing mass and the kinematical mass, they are very different, more than 120%. So huge violation of the equivalence principle. For very large halos, you don't see violations of the equivalence principle. For halos of 10 to the 15, basically you recover general relativity. So there's no violation of the equivalence principle. And now you know probably why. It's because when we are in small halos, the screening mechanism is not effective because the density is so low that the galaxies in halo feel a very strong fifth force, so they move really fast. So the dynamical mass is much larger than the lensing mass. But when you come to halos of 10 to the 15, these are huge halos, very massive, very dense. What you have is that the fifth force is completely screened, and so the lensing mass and the dynamical mass are the same. So you satisfy the equivalence principle. And I should say that these models, even the one which have such a big violation of the equivalence principle, these same model parameters, they satisfy all the tests that I showed you before. So if you do an experiment in laboratory to measure the equivalence principle for a symmetry model with this parameter, you don't see any violation of the equivalence principle. The background evolution of the universe is also very similar to lambda CDM. The very large scales structure formation of the universe, linear large scales like the cosmic microwave background radiation, the linear matter Bohr spectrum, also you cannot distinguish this symmetry model with lambda CDM. But if you look at this particular test, you can see the deviations are huge. So this is a fantastic test to try to put constraints on symmetry models, try to rule out these theories, in fact. At least put constraints on the model parameter. Or maybe to have a smoking gun that could be detected. Now there's something else, and again the signature for smoking guns in screening mechanism is this slope here. That is something that only the screening mechanism can lead to. So the other, I don't know what the time is. Okay. Another thing that we can do, another way of measuring masses in our universe, astrophysicists use, is using the thermal mass. So the thermal mass is basically using X-ray satellites now, like the Chandra that I showed you yesterday. So they can measure the profile of the hot gas in the intergalactic medium. And from the profile of the gas in the galactic medium, they can extract what's the pressure of the gas. And then from hydrostatic equilibrium, you know that the pressure of the gas should withhold basically the gravitational force, just like in a star. A star does not collapse because there's the pressure of the gas. So in a galaxy cluster is the same. So the mass of a galaxy cluster also should withhold, with the gas should withhold the hydrodynamical pressure. Now, if we have a modified theory of gravity, the gas will be hotter, because faster, due to the existence of this fifth force. And that means that the mass that the cluster can have will be enhanced again, will be much larger. Because now the gas is hotter. If it is hotter, it means the star or the galaxy cluster can be larger and support more mass. So we can also do this kind of measurements and compare the thermal mass with the lensing mass. Will be another way of testing the equivalence principle in there. And I will very quickly, just so we have very similar results. But something I would like to ask again is, this is another very nice test to ask the question, okay, up to now, I have a universal coupling between my scalar field and all the other fields, the standard model fields and the dark matter particle. What if my scalar field couples to the standard model fields in a different way that it couples to the dark matter? Because they are different fields, so there's no reason that they should be in the same age group. So they can have different couplings to different particles. So when I'm doing the analysis of measuring mass of clusters for using thermal methods, what I'm doing is that I am basically measuring how baryons are sensitive to this fifth force. When I'm measuring the dynamics of galaxies in a cluster, what I'm doing, I'm measuring how the dark matter basically is sensitive to the fifth force. So basically I can calculate ratios and comparing what's the mass of a cluster from thermal methods. So basically I'm saying what's the mass of the cluster if there is a fifth force coupling to baryons, or whether there is a fifth force coupling to dark matter. And I can also do this kind of tests. Okay, since I'm quite late, I wanted to, and we can talk about that if you're interested. So this is not just pure theoretical tests. I can use constraints from observational data. So we went to the Slow and Digital Sky Survey catalog, because in there, people have been collecting data from galaxy clusters, and they measure the galaxy cluster using lensing methods. So I have the lensing mass. They have been measuring the mass of galaxy clusters using dynamical methods from velocity dispersion. So I have the kinematical mass. And also in there, I can find measurements of galaxy cluster masses using thermal methods. And some of these clusters, they have calculated using the three methods. So I can use this data to put constraints on my gravity models. And these are basically these two black lines here. Here I'm just showing for the f of r model. Now you remember. And basically using the thermal mass and the lensing mass and dynamical mass, I can say basically that this f of r theories with 10 to the minus 4, even 10 to the minus 5, they are almost ruled out. Only the f of r gravities with 10 to the minus 6, they are still viable using these methods. And for the symmetron, there's also a similar plot, but I'm not going to show it now. Okay, so these methods are still not very accurate, but at least they can start ruling out some of these theories. Okay, so the next question that appears is that there are many, it goes back. So there are many screening mechanisms, as I showed you before. So the question is, how can we distinguish between them? And this is the last part of my talk, yes? Which one is the screening mechanism that the universe has chosen to, if there is modified gravity, to screen away your modified gravity? For that, we need to look at very specific properties of the screening mechanism. So the symmetron has a very specific property, which is this symmetry breaking potential, and that leads to the creation of topological defects. So here I'm showing you a simulation, a box, where I'm showing the value of the scalar field in different parts of the universe. So this is a box of the universe, so this is filaments with the halos, dark matter halos there, there's the red dots, and then there's filaments, these are the blue dots. And the symmetron, basically, in the voids, as you can see, will take a vacuum expectation value, as we know from the symmetry breaking. And in some places of the universe, this vacuum expectation value will be the red part, and in other parts of the universe, the symmetron will take, for instance, the positive value of the expectation value. So what does that mean for those who do particle physics and high energy physics? Is that in between these regions, you will create what is called domain walls. And this is a picture of the symmetron domain walls that are created when the symmetron breaks the symmetry. Now, domain walls, they leave a signature in our universe on structure formation and on also gravitational waves. Because these domain walls, they will collide, and so they will merge, they will disperse, and they will create gravitational waves. Now, for general relativity, so for that it means you need to solve the gravitational wave, the tensor perturbation for the metric, and the gravitational waves in general relativity is just quite simple. It's basically given by that. With Hij, basically you only have two polarization modes, and you have the Hubble factor that dumps a bit the amplitude of the gravitational waves. For modified theories of gravity, this equation becomes a bit more complicated. So you can have extra polarization modes. The fact that you have a scalar degree of freedom there now changes the polarization modes. You can have some frictions which change the Hubble friction. You have a modified propagation speed. You might have a graviton mass in case of massive gravity theories, which will change also the dispersion relation gravitational waves. And in particular, you can have non-zero source terms. And this is what, in fact, I want to focus is in these non-zero source terms. Because if you have domain walls, these domain walls will source the equation for the gravitational well in a different way. So for the case of the symmetron, this is what I'm showing you here. Here is a simulation where you can see the value of the symmetron field. The red one is the field in one minima. The blue one is the field in another minima. And in between, that's the domain wall. As you can see, the domain wall, they move, they change, they split, they separate. And as it goes, this happens. This is the value of the amplitude of the gravitational waves in there. Yeah? So we will create these domain walls all over the universe. They will create a stochastic background of gravitational waves. And with PTA and the nanograph, the idea is that maybe we can measure this stochastic background of gravitational waves. So what we can do is basically to run simulations for different symmetry models. For instance, this is a symmetry model where the Compton wavelength of the field is very large. So you have very large domain walls, very large domains. The range of the field force is very large for the student. That's the Compton wavelength. While here, the Compton wavelength of the symmetron is much smaller. So the domain walls are a bit smaller there. So different symmetron parameters leads to different masses of my scalar degree of freedom, and that leads to different patterns of the gravitational wave. So you can see the stochastic background of the gravitational waves here is very different from there because we are looking at different couplings, different mass ranges for the field, etc. And so the whole idea now is basically to try to see what is the power spectrum of these gravitational waves and the amplitude of these gravitational waves and try to compare with data. So we try to do that for the nanograph. I'll just show you what would be the nanograph here, which basically puts a very loose bound on the slope of the amount of gravitational waves that we can have in the universe. So these are the different symmetron lines here. The large-scale structure information also has some background of gravitational waves, very, very small. Supermassive black holes will be somewhere here. And we can't do much, in fact, at the moment, because the nanograph range of frequencies is quite far away from the range of frequencies that the symmetron domain walls produce, these gravitational waves. So we cannot use this data, but hopefully in the future, we'll be able to use also stochastic background gravitational wave measurements to put constraints, maybe detect this kind of screening mechanism or rule them out these kind of theories. Okay, well, thank you very much. I think I'm a bit over my time, but that's what I wanted to tell you about. Thank you.
Okay. Any questions from the audience? Please. Okay.
About symmetron, they have a phase transition, right? But I'm not sure how about redshift that phase transition occur because it depends on gravitational wave from the very early tableau to us, right? So that it can it affects during this.
Yes, very good question. Yes, I rushed through my last part of the presentation. Yeah, very good. So the symmetron, the phase transition is very, very late. It's usually at redshift 2, 1, because it's like a dark energy candidate. So the phase transition happens very late. So the energy scale of these domain walls is very different from the primordial domain walls and topological cosmic strings that can appear, for instance, after inflation, like on the usual phase transition that we have in the standard model particle phase. So it's very late domain walls, and the energy trapped in them is also much, much weaker than the usual ones. Otherwise, if you have these kind of domain walls, they would spoil the CMB spectrum, for instance, or structure formation. So the way that the symmetron doesn't spoil it is because it's very late, as you said. That's a very good point. And also the energy trapped in these domain walls is quite low. Yeah. Thank you.
Okay. Anyone else? Okay.
Okay. Thank you for the nice talk. My question is, since the screening mechanism work well around the high curvature region, my question is, should the effect of should the theory of my modified gravity have no effect on the region or on the region around black hole?
So if I understood you well, you're asking whether this series of modified gravity would affect the mergers of black holes,
yes,
and then the signature. Well, in fact, they do affect a little bit, yes. So I think, well, it depends on your choice of the model parameters. If your screening mechanism is very effective, then the scalar field just completely decouples from matter. And so as you go to the final stages of the merger of black holes, you only release energy through the gravitational wave. If, of course, in other ranges of the parameter space, the screening mechanism is not so effective, and then you have the usual scalar tensor theory where we already have very good bounds on the existence of scalar fields, you know? So then you go into a region where it's already ruled out. So the models that I showed you here, and I'm presenting the simulations, are models where they pass all the gravitational wave constraints. So they screen well before curvatures of black holes or pulsars. So in fact, these symmetron models, they screen at the density of a galaxy. So that's much, much lower than the density of black holes. So as you go to a black hole scale, this field have already completely decoupled from matter. So yes, those are the ones I'm saying. But of course, we have other scalar tensor theories where they leave signatures in gravitational waves, and yes, and many of them are ruled out. In fact, yeah.
Oh, okay.
Yes.
And, yes, thank you.
Thank you for the question. Yes.
And okay, can we estimate the effect of fifth force on the temperature of gas around the cluster for various mass? Because can we do this? Because if cluster have different mass, the effect of screening mechanism is are different, right? So I think that the temperature allow the cluster should be changed due to the different effect of fifth force. Right?
Yes, that's right. Yeah, that's a very good question. Yes. So we, yes, I didn't have the time, so we did some studies, some simulations with gas in our simulation. So we put gas, and we saw that the gas was much hotter, and so the gas profile in within the symmetron models and FOR gravity models and even DGP, they are hotter, so it changes quite a bit from the general relativity one. Now, I didn't mention here, well, because I didn't have time, but also there's a problem there because we don't know if the gas is hotter because of the symmetron, the fifth force, or because we have some kind of dark matter component which would make, you know, the gas molecules rotate faster, or the profile of the dark matter would be different. So the degeneracies there are much stronger. Also, when I start using gas, we have to take into account, you know, AGN feedback effects, supernovas that go off. All these will heat up the gas as well. So the physics, the gas physics of the astrophysics is much more complex. So it's a less clean signal of modified gravity. But for sure, if one day we can understand very well all the baryonic gas physics at galaxy scales, then we should look at gas profiles and how hot they are to try to see if we can probe these fifth forces. Yes.
And for the last question, how much the difference between the length scale at which the fifth force should effective and the length of the radius of the large cluster of galaxy, I mean largest cluster of galaxy, compare the length of the length scale at which the fifth force should effective and the length scale of the compare with the length at which the fifth force should effective and the radius of the largest cluster. I mean, can we compare to this? Because I just to get some feeling how about the distance of the scale of galaxy and scale of fifth force.
Yes, no, that's a very good question. So yes, so the length scale is about megaparsec scales. So in these simulations, we used about 1 megaparsec for the Compton wavelength of the symmetron. And a galaxy cluster is about megaparsec scales as well. 1, 2, 3 megaparsecs. It depends on the size of the galaxy cluster. Some of them are smaller, some of them are larger. So the length of the fifth force is basically around the length of galaxy clusters. And that's why, the effects are so strong in galaxy clusters.
And usually we take into account the effect, the void effect of void in the universe. What is the radius of the void? Do you have?
Yes.
Mm.
I see you didn't come to my last lecture yesterday. I showed the voids. Yes, very good. So in my last lecture, I mentioned the voids. So voids are a fantastic place to test modified gravity because the fifth force is not screened. Yes. So then the force should be very active. So usually voids are very, very big in modified theories of gravity, larger than lambda CDM, and they are emptier. But voids can go from scales of 5 megaparsecs all the way to 20, 30 megaparsecs. So voids usually are larger than the allowed region of the parameter space for the symmetry model. And the allowed region is about 1 megaparsec for the range of the force. Voids can be 20 times, 30 times larger. So yes, but voids are very good places to test gravity, to see if the fifth force is there. But as I said in my lecture, the problem with voids, we don't have much matter there. So there are not many galaxies, so we can't see, the effects of the force because they are voids, yes, they are empty. So it's very difficult to do experiments with voids. But people try to see like the size of voids, the abundance of voids, but still the data is not very good. Yeah. But that's a very good question, yeah.
What is the distance between us and nearest void? Can I ask this? The distance between us and nearest void?
The distance to the nearest void?
Yes.
I don't know. From here, from this room? Sorry, I don't know, Kampi. I don't know what's the nearest void here. No, sorry.
Thank you.
Sorry. Yes. But I think it's going to be more than a megaparsec. I think it's more than a megaparsec, Kampi.
Okay. First of all, I didn't participate in your lecture, so I will ask you as a layman. My question would like overlapping with Ajahn Kampi that I would like to know at which scale this model actually work. I mean, we know that there are some scale that we should modify the GR, like the galaxy cluster, or even in the galactic scale where the rotation curve of star around the galaxy is deviated from the GR. But you result here try to like probe into the galaxy cluster. Would it that used in the galactic scale as well?
Yes, very good question. Yeah, I can see you didn't attend my lecture. No, so yes, I should have been clear. Sorry, I gave the colloquium assuming people attended my lectures. So I should have said, in fact, that this symmetry model is an alternative to dark energy. So the scalar field will drive the universe acceleration. So the symmetry breaks at redshift 1, 2, 1, yes, around that. So it's a very late phenomenon. So dark matter, in my case, is just a massive particle. I'm assuming that there is cold dark matter in the universe. So all the galaxy rotation curves, etc., that is solved by a cold dark matter component. So the symmetron is just a dark energy model where there are interactions with standard model fields and the dark matter in itself. So it doesn't solve the dark matter issue. Yeah, dark matter is there in my simulations.
I have seen you deriving the gravitational lensing by using the perturbations. Like, I just wondering, like, if I doing the second order perturbations, would I expect that the gravitational lensing to be more or less than the usual one? Yeah.
I didn't understand your question. What you're asking is?
Sorry. I have seen that you deriving that like the gravitational lensing is unaffected by the first order perturbations. So I just wondering, like, how about the second order perturbations? Would I expected the gravitational lensing to be more or less than this one? And is it possible to obtain this kind of data, or is it too small to detect it?
No, it's a very good question. So, as I said in my lectures, even at galactic scales, the Bardeen potentials, the two potentials that come in the metric, they are of order 10 to the minus 5. So if you linearize the gravitational part, not the matter part, the matter can be several orders of magnitude larger than the critical density of the universe. But the Bardeen part, the Bardeen potentials, those you can linearize them. And the lensing that I'm talking about, it's basically weak lensing. So it's lensing at galaxy cluster scales. So first order linear perturbation theory, it's perfect, works very fine. It's true that now if you go to strong lensing regimes, then like if you try to probe lensing of black holes or compact objects, etc., on much smaller scales, then you have to assume go to second order or go to the fully nonlinear equations. And in there, they are not the same, because if you do that, then even in conformal field theories, in conformal gravity theories, the Weyl potential is not the same in GR and in these modified theories of gravity, because in particular, we have the scalar field perturbations, so which source also the other potentials in a strong way. And you have other modifications. So, but at galaxy cluster scales, we don't care about that, because the effect is really small. And the matter is basically dominated by cold dark matter and the baryons in there. So linear perturbation theory is more than enough at galaxy cluster scales. If you want to go to much smaller scales, compact object, no, then you need to go to second order perturbation theory, or even look at really nonlinear effects. Yeah.
I see. Okay. Also, I have another questions. I was just wondering about like the gravitational wave. So you said that like at some scales there is like the fifth force available, right? Is that affect the gravitational waves at that Compton wavelength?
I didn't understand. Can you?
Oh, sorry. Like you say that at some scale, like there is a fifth force available, right? Is that affect the gravitational wave at that Compton wavelength? Like if I have a gravitational wave at that wavelength, is that affected?
No. So for the gravitational waves, you don't need to think about fifth forces. For the gravitational waves, what you have is that they appear because you create domain walls. So this is something independent from the fifth force. So in chameleon models, like in the FOR gravity model, you don't have this effect. You don't change the gravitational waves, for instance. Well, not at the stochastic background level and the large scales. So in this model, you create this effect of different background of gravitational waves because you have domain walls, these topological defects that appear because the field takes one minima of the vacuum expectation value or the other one. And then you create these domain walls, and these domain walls, because they are dynamical, they collide, they burst, they merge, they are a source, that's the equation, they are a source for my gravitational wave, for the tensor perturbations in the metric. It's independent of the fifth force. For instance, there are, even in the standard model of particle physics, these kind of gravitational waves, they appear, and there's no fifth force, there's no scalar tensor theory. Just because in standard model of particle physics, you also have phase transitions. But those gravitational waves on the standard model of particle physics, they happen at the high energy early universe. This one is at redshift 2, 3, 1. Yeah.
And also, I just wondering about like, is it possible that like the symmetron absorb the gravitational wave and the potential just go back to like the to the another side? Is it possible?
Yeah. So the field switching sides.
Yeah. Is it possible that I have the strong gravitational waves and it could like absorb like this field could absorb the gravitational waves and it changed the side at like a distance.
Yeah, yes, that's why these domain walls, they collapse when they merge, they burst. So in those things, you sometimes you see, maybe not, but sometimes you see in the in the simulations that the field will, it's here completely red, but then it might become blue. You see? Oh, okay. So it means that the field switch sides on the minima. Yes, that's what will happen maybe here, I think.
Oh, I
So
see.
the field here is one minima, there is another minima, and there it switched sides in there. Yeah.
I see. Okay, I understand now. Okay, thank you.
Okay.
I just would like to know at which order or magnitude that can this signature of gravitational wave can be detected? I mean, in the future or very far future?
Is more on the very far future. Yes, more on the, because these so while the gravitational waves that we produce in the early universe, they are quite strong, and they leave a signature which all these, all these experiments are built up to try to detect them. This is a kind of a gravitational waves that come on a completely different frequency, very, very much lower. So maybe the Einstein telescope, which is supposed to come in 2037, 2040, something like that. I don't know if it comes. So yeah, maybe for you. Maybe for you.
Okay. Another quick question. So this kind of signature come from the fact that the scalar field is a real scalar field, right?
That's
And-
right.
And what about we change it into complex scalar field? This would not happen. And would it change your model in
Yeah,
general?
so if it is a complex scalar field, you will get cosmic strings. So you don't get domain walls as topological defects. The other topological defect that you get is a cosmic string. Because if it's a complex field, then you'll have a U1 symmetry. So it's not just two minima, but you have kind of a circular rotation on the minima. And then you get cosmic strings. And cosmic strings also source gravitational waves, in fact. But it will be a different signature. That's right. It will be a different signature.
Well, I want to continue Campi and Peng with earlier question. Hello. Oh, I want to continue Campi and Peng with earlier question. About the scale, I mean, your example is in the galaxy cluster, right? And in the center of galaxy cluster, they have last fifth force and compare with the outer. And also Pengwei's question is galaxy, you say this model is not for the dark matter case of the galaxy, right? But is it possible that the modification not depends on the local density, but it depends on the difference of the density? I mean, something like delta law is not depends on the local density, but depends on difference of this kind of region. So maybe it is possible to explain both.
Yeah, that's a very good question. Yes, and I think you're right. In fact, even these ones, they could depend on the gradient of the density. So if you have a density profile, for sure you will change the fifth force. The fifth force is not going to be, because I gave you the feeling that the fifth force is on or off. Yes, and the reality is not like that. The fifth force is not on and off. It's not like screen or unscreen. The fifth force like slowly changes, and of course, when you go to galaxies scales and even cluster of galaxies, you have a distribution of matter. So you have, even within the galaxy cluster, you have a galaxy, and then you have a void, and then you have another galaxy, you have voids, and then you have gas with a given profile. So things are a bit more complicated than what I've presented. I'm not aware of a model where screens through gradients of density. I don't know. The models that I'm aware, they usually screen on the mass. For instance, the Weinstein mechanism, or basically at the moment you set up a mass scale, you have a radius called the Weinstein radius, where the whole region around that radius is screened. There is no fifth force, basically. For the chameleon and the symmetron or dilaton, it's basically a threshold on the energy density. It's just the density of matter. I know there's a model which screens in terms of pressure, the amount of pressure that matter has as well. But in terms of gradients of densities, I don't know any model. But for even if there's no model that screens with gradients, for sure, if you want to do a proper, very precise analysis, you should take into account the profile of matter always. There. No.
Okay. Any one or any more question? No. If no, then let's thank David again for a wonderful talk.
Thank you.
Okay.
Thank you. Thank you.
All right, then I think that's it for today, and stay tuned for the next colloquium. Bye bye.